All right, so in this section, we are really going to simplify our lives a lot. And this is fantastic that we got here. So, this is section 3, differentiation formulas. Okay. And I want to start this by looking at a previous problem. So, back in section 1, we were asked to do this problem here, which is find the equation of the tangent line to f of x equals x to the second minus 8x plus 9. And then we were asked to evaluate this at x equals 1 so we can find this tangent line that we were interested in. And anytime you need an equation of a tangent line, remember you want to first find a point, second, find a derivative, and look at all this work we had to do for the derivative. Okay? I'm going to zoom out here just so you can see all the work that we had to do for the derivative. So give me 1 second. It's all right here. So I'm going to block this in for us. All right, so that is all the work that we had to do just to find this derivative. All right? In this section, I'm going to show you a lot of different formulas that we can use. All right. Now, I'm not going to go through and prove these. They're proven in your book. Definitely check that out. But what I want to do is just give us the formulas. That way we can go ahead and start looking at more complicated problems, and finding derivatives are going to be so much easier for us. So, the first derivative formula that I want to go over, all right, is called the derivative of a constant function. So, we got the derivative. Oh, that marker's real big. All right. So I will do this in both notation just so you can see it. So the derivative of a constant function is nothing more than this. All right. If you wanted to find a derivative of a constant, well, that derivative is equal to 0. Now in Newtonian, it looks like this: f prime, or if f of x equals c, then the derivative of c is going to equal 0. Now, if you think about this, and I think it's easier to look at this in terms of Newton rather than Leibniz. So, if you recall, f of x sometimes is just really fancy way of writing y equals c. Now, let's say y equals 5. Well, we know, according to the xy chart or xy Cartesian coordinate plane, that is nothing more than a horizontal tangent line, or a horizontal line, 1, 2, 3, 4, 5, at y equals 5. So it would look something like this. We also know that the slope of all horizontal lines is equal to 0. So naturally, the derivative, which is the measure of the rate of change at a specific value, is the slope, should also equal 0. So the derivative of a constant equals 0. So some examples would be, let's find the derivative of 5. Well, that's just going to equal 0. How about if y equals pi, find y prime? Well, y prime is going to equal 0 because pi is a constant. Okay? Even something like this. Let's find the derivative of -2. Still, it equals 0. All right? Excuse me. So, the derivative of a constant, super easy. Okay? Now, we're going to transition into power functions. Okay? So, power functions have the form f of x equals x to the n. All right? Now, the easiest example here would be if f of x equals x, find f prime of x. Well, once again, we're going to rely on our intuition here. Remember, f of x is just really fancy writing for y. So we have y equals x. We know that if we were to graph that, now I need to be a little bit more specific here. So If we were to graph this, this is nothing more. All right, this is nothing more than a line that crosses through the origin where every value of x is the exact same value as y. And we can easily identify the slope of this because the slope would be 1 over 1. So f prime of x equals 1. Now, this is a very special case, okay? Because it's real intuitive. We can see that. However, it's not as intuitive if you were looking at, let's say, this example. If f of x equals x to the second, find the derivative. All right. Now, remember, like I said, it's not as intuitive because if you look at f of x equals x squared, it's a parabola, it's a curve. And we know the slope, let's say at this point, is entirely different from the slope at that point right there. They are two completely different slopes. So the slopes are constantly changing. In the previous example, that slope is constant. It's always going to be 1. All right. So what we have here, and I'm just going to give it to us, all right, because I think it's, just important to have it. I'm going to give you the power rule. So here's our second rule. Now the power rule is really nice. So if n is a positive integer, then the derivative of some function of x raised to an exponent is equal to n times x to the n minus 1 power. So by looking at our two examples that we previously did, if I wanted to find the derivative of x, well, note that this is x to the first. So according to this derivative, according to the power rule, I take the exponent, which is a 1, and I pull it out front of the variable x. And then I subtract 1 from that exponent. Now we know 1 minus 1 is 0. And as long as x does not equal 0 here, x to the 0 is 1. And 1 times 1 is 1. Now let's see how this applies to the second example that we did. So if we wanted to find the derivative of x to the second, all we have to do is take the power, put it out front, and subtract 1 from that power to give us 2x. And that is your derivative. So if we go back to that, well, you know what? Let's do a couple more of these. All right. I don't want to go back to that problem yet. All right. So let's do a couple more of these. If h of t equals t to the 1000, find h prime of t. Well, once again, h prime of t, you would take the exponent, pull it out front, and then subtract 1 from it. So h prime of t is going to equal 1000 t to the 999 power. All right, so I hope you get the gist of what's going on with the power rule. It's very easy to apply, okay? Now what we're going to do is we're going to transition into new derivatives from old. In other words, we're going to start to apply some more rules here. So the next rule I want to go over, all right, this is our third rule, is the constant multiple rule. Now, these are just little things that really help us out, and it makes our life a little bit easier when it comes to finding derivatives. So, if c is a constant, and f is a differentiable function, then what you are allowed to do is this. If you're taking the derivative of a constant multiplied by some function of x, you can take that constant, pull it out front of the derivative, find the derivative of the function, and then multiply the constant by everything. Okay? Now, there's a lot of things going on in this constant multiple rule. First, we need to understand differentiable function. Remember, differentiable means it's a nice, smooth, continuous curve. Okay? There are no cusp, there are no jump discontinuities, there are no vertical tangent lines, nothing like that. It's just nice and smooth, Well, not like that, but nice and smooth, okay? Second, if you have a constant that's multiplied by some function, I think we need to see what that looks like. So an example of that would be like this. Let's say I wanted to find the derivative of 3x to the 15th. Okay? Well, technically, what I can do is this. I can say, I'm going to take that constant multiple, put it out front of my derivative operator. I'm going to focus on finding the derivative of x to the 15th, which is going to be 15x to the 14th. And then finally, take 3 times 15, which is 45x to the 14th. So that is what our derivative would be. So when you look at it, it's not that bad, okay? It's just, if you want to, you can kind of like pull it out front, find the derivative of the function, and then multiply. But sometimes, and you will definitely get like this. Sometimes if you have, let's say, p of x, which equals 1/2 x to the second power. Normally what people would do, if they wanted you to find the derivative, you would just say, well, the derivative equals, take the power, pull it out front. So this would be 2 times 1/2 x to the first. And then you would simplify this just by reducing the 2's to give you the derivative is equal to x. And that's it. So if you want to, you could really write this out. I encourage you to do that until you get really comfortable with this. Okay? The fourth rule is the sum. Actually, I'm going to combine them. Your book separates them. I don't know why they always do this, but it's going to be the sum or difference rule. All right? And what this says is basically this. If f and g are both differentiable, then the derivative of f of x plus g of x is going to equal the derivative of f of x plus the derivative of g of x. And then if I use a different color, you can also put a minus sign in there as well. It's the same exact thing. Okay? If we're using prime notation, meaning, Newtonian notation, we write it like this. So this would be the sum rule. And we would just say the derivative of f plus the derivative of g. And the same applies if you were subtracting these two functions as well. Now we can get into the problem that we discussed at the very beginning of class, which is this problem right here. All right. So we have f of x equals x squared minus 8x plus 9. So here's an example. If f of x equals x squared plus 8x, was it plus 8x? Nope. Minus 8x plus 9. Find the derivative. Well, with this, I'm going to be applying all the rules that I've learned. I'm going to be applying the power rule, the sum and product rule. The sum and difference rule, the constant rule, and the constant multiple rule. I mean, they're all going to kick in. So I'm really going to write this one out first just so you can see it. So what I want to do here is I want to differentiate x squared minus, I want to differentiate 8x plus, I'm going to differentiate 9. So right there is my sum and difference formula, or my sum and difference rule. Now, if I wanted to break this down even further, the derivative of x squared is going to be 2x minus. Now, technically, I could have taken that 8 and put it out front. So then the derivative of x would be 1. So this would be 8 times 1. Plus, we know the derivative of a constant is 0. And if I just simplify this real quick, notice I get 2x minus 8. Now, let me go back to the other problem. When we use the definition of our derivative, this is the definition of the derivative. Look at how much work it took us to get all the way down to right here. 2a minus 8 is the same exact thing as 2x minus 8. So it really, really, really helps us to know our formulas. Because I did this in one step versus all of that algebra. All right. Remember at the very beginning of the semester, I said, listen, computationally, calculus, it is, the calculus step computationally is not that bad. It's the algebra associated with everything after that. All right. So the last rule that I want to go over, I think is the last rule, is going to be, no, there's two more. All right, is going to be the product rule. Now, the product rule is definitely a special one. All right, so I'm going to put a big star next to this. All right, so if f and g are differentiable, then the derivative of f of x multiplied by g of x, hence the product rule, is going to equal f of x times the derivative of g of x plus g of x times the derivative of f of x. Now, the nice thing about the product rule definitely follows the commutative property, meaning that it doesn't matter how you write this because you're multiplying and adding adding things together. The only thing that matters for us is that you label everything properly. All right. So let me go ahead and do a couple examples of this. All right. Like I said, it's very straightforward. So let's go ahead. Let's find the derivative for 6x to the third times the square root of x. Okay. So the hardest part about this is just being able to recognize that you have two functions of x. The first one is right here. We're going to call this f. And the second one, we're going to call this g. All right. Now, in prime notation, the product rule is very simply stated as such. All right. It's way easier to understand. And this is the preferred notation. Okay. So all I'm going to do is I'm going to label things. If you look at the product rule, notice that on the right-hand side of the product rule, we have f, we have f prime, we have g prime. So what I'm going to do is I'm going to write f equals 6x to the third. F prime, I use my power rule. That's going to give me 18x to the second. G is going to equal x to the 1/2. Therefore, g prime is going to equal 1/2 x to the negative 1/2. Now, I definitely went fast there. So I'm going to show you what happened. If you wanted to differentiate the square root of x, notice all of our rules that we have, none of them has dealt with a square root. It's been a constant, it's been a power, it's been a constant multiple, and it's been functions. But it's never been the square root. So we need to go back and we need to rely on our algebra. Hopefully we remember that the square root of x, this is raised to the first, the index would be a 2, hence the name square root. So another way to rewrite the square root of x is x to the 1/2 power. It follows this rule that we learned back in algebra. Therefore, if I wanted to differentiate the square root of x, the first thing I have to do is I'm going to have to rewrite this as x to the 1/2 power. Now, when we differentiate it, this is a power rule, so we could take the power, put it out front, and subtract 1 from that exponent. I was just really clever on how I wrote the number 1. I wrote it as 2 over 2, so I can have a common denominator. And 1 minus 2 is negative 1/2. And that is how I got 1/2 x to the negative 1/2. All right, so back to here. If we go ahead and we find this derivative using the product rule, since I labeled everything, I'm just going to do it again. F g prime plus g f prime. And then I just come directly underneath and just make my substitutions accordingly. So f is going to be 6x to the third. G prime is going to be 1/2 x to the negative 1/2. G is x to the 1/2. And then f prime is 18 x to the second. Now, what we really have to be careful about is how do they want us to write our answers? Normally, they like positive exponents, things that are simplified. Okay? So, like, for example, the first half of this is going to turn out to be 3 x to the third over the square root of x plus 18 x squared square root of x again. All right? It's always good to read the question in its entirety, including the parentheses, and they'll tell you completely simplify, write your answer as an exact answer. That means no decimals. Or it'll just say set up, do not simplify. If the directions say set up, do not simplify, that's this right here. This is the set up, do not simplify. Okay? If the directions say simplify, well, this is what you're working with right there. Okay? So you do have to be careful about how you type in your answer. You got to make sure that you're reading this correctly. All right? I'm going to go ahead and do another example with the product rule. So here's another example. Find f prime of x for f of x equals the cube root of x times 2x plus 1. So once again, let's go ahead. Let's label. Here's our first function. Here's our second function. All right. I know the product rule, which is f g prime plus g f prime. So f is going to equal x to the 1/3. Make sure you got to rewrite that. Cube root of x is x to the 1/3. F prime is going to equal 1/3 x to the negative 2 over 3. G is 2x plus 1. G prime is just going to be 2. And then we just make our substitution. So f x to the 1/3 times g prime, which is 2, plus g, which is 2x plus 1, times f prime, which is 1/3 x to the negative 2 over 3. And if you just wanted to write this, so there's positive exponents, this would be 2 times the cube root of x plus 2/3. Sorry, that's bad math. 1/3 times 2x plus 1 to the x to the negative 2/3. And then to write that as a positive exponent, you would just write this as 2x plus 1 over 3 times the cube root of x squared. Now, the final rule that we're going to go over is called the quotient rule. Now, the quotient rule, I will warn you, it gets messy very, very, very quickly. All right? So you do have to be careful with the quotient rule. Order matters with the quotient rule. I don't even remember what rule we're on right now. Is this 6, 7? Let me see here. 4. Product rule would have been 5. I just put a star next to it. All right, and here's 6. This is the quotient rule. And here, order matters. Okay, so make sure you are labeling correctly. So if f and g are differentiable, then the derivative, and I'm just going to write, without the function notation, I'm just going to write it as the derivative of f over g is going to equal g times f prime minus, put a bracket or a parenthesis, f times g prime all over g squared. Now, your book will not show those brackets that I put in there. You want to make sure you put them in there, okay? Because you don't want to forget if you got to distribute that minus sign. You don't want to forget about doing that, all right? So here's an example, right here. Find p of t, or find a derivative of p of t for p of t equals t to the second plus t minus 2 all over t to the third plus 6. Now, what makes this so hard is the algebra associated with it. So let me go ahead. The numerator, well, that's f. Denominator, that's going to be g. So f equals t squared plus t minus 2. F prime is going to be 2t plus 1. G equals t to the third plus 6. G prime equals 3t to the second. Now, we need our quotient rule here. So like I said, just you got to be really careful about where you put things, all right? So p prime of t is going to equal g times f prime minus, make sure you put that bracket there, f t squared plus t minus 2 times g prime, 3t squared, all over, I could put in parentheses, t to the third plus 6 quantity squared. All right? Now, from here, it's just a matter of grouping like terms, using algebra, factoring if you can, trying to simplify some stuff. But I'm going to leave that to you. What you should get at the end of the day is negative t to the fourth minus 2t to the third plus 6t to the second plus 12t plus 6 all over t to the third plus 6 quantity squared. So that'll be like a nice little algebraic exercise for you to do. Now there is one nice thing, okay? In your book, at the very end of this section, they do have a nice table of derivatives for us. So I literally just went to your book here. Oops, sorry. Let me zoom out just a little bit. There we go. And here are all the formulas right here that we just learned. Okay, none of them are labeled though, but you got to know their names. So like for example, this very first one right here. All right, highlighted for us. That's the constant rule. This one right here, that's going to be the sum of two functions. All right, the sum rule. Here, all right, is our power rule. Here, in pink, that is the product rule from left and the quotient rule on the right. All right, and like I said, you got to know these rules. Okay, so what I want to do here is I'm just going to do a bunch of examples of derivatives. All right. And I'm going to tell you the rule that I'm going to be using, but you got to practice this. The assignment that I uploaded has a lot of problems on it because it's so important that we know how to find derivatives. Like this section is pivotal for us to know. You got to master this section in order to be successful in the course. All right, so let me go ahead. Let's get back to our notes. And like I said, I am just going to be doing just a bunch of examples here. Okay. So I'm going to kind of move a little quickly, but that's okay because this is a video and you can pause it and you can always just go back and find it. So find the derivative for the following functions. All right. And as I go through this, there's going to be certain things I do. So make sure you are following along and you're catching what I'm doing. All right. So the first one, f of x equals 2 to the 40th. The derivative is 0. Why? Because 2 to the 40th is a constant. It's what it is. 2 to the 40th power is a huge number, but it's a constant. And the derivative of a constant is 0. Number 2, f of x equals pi to the 4th. The derivative equals 0. Because once again, pi to the 4th is 3.14 and a bunch of decimals after that, but it's still a constant. And constants are always equal to 0. They're derivatives. All right. Number 3. I'm literally just taking these out of your book. G of x equals 7 over 4, x to the second, minus 3x plus 12. My derivative. All right. For the first, I pull the 2 out front. Subtract the exponent from 1. For the middle, that's just a linear function, so it's going to be minus 3 plus 0. And finally, I just clean this up a little bit. That's going to give me 7 over 2, x minus 3. Okay. Keep moving here. Now, this is a nice problem here. This really demonstrates what's happening with the product rule, okay? Sometimes you get lucky. So if we look at a situation like this, I'm going to do this two ways. The first way, I'm going to use my product rule, all right? So here's f, here's g. All right, so we have h of u equals the quantity 3u minus 1 times the quantity u plus 2. F is 3u minus 1. G is u plus 2. So I'll just write f equals 3u minus 1. The derivative equals 3. G equals u plus 2. My derivative here is going to be a 1. I know the product rule is f g prime plus g f prime. So f is 3u minus 1 times g, which is 1, plus g is u plus 2 times f prime, which is 3. Now I will go ahead and simplify this by using my distributive property. So I get 3u minus 1 plus 3u plus 6. And this simplifies down into 6u plus 5. So h prime of u equals 6u plus 5. Now, I gotta be honest with you. Sometimes it helps to do some algebra first. Let me show you. H of u is 3u minus 1 times u plus 2. So if I wanted to, I can simplify this. So I'm going to go ahead and use my vertical addition method, which a lot of people confuse this with FOIL. And I hate the word FOIL. FOIL is so bad because it only applies to this specific type of problem. The vertical addition method applies to everything. So underline the 3u and distribute it. You get 3u squared plus 2u. Now we're going to underline -1, and we're going to group as we go. So we're going to distribute that. -1 times u is -u minus 2. Therefore, h of u equals 3u squared minus u, plus u plus 2. And everybody should be yelling at me because this is 6u. And when I group them together, it's my 5u. Sorry, I've been doing this all day, and it's already 8:19 at night, so I'm pretty tired. But anyways, now, if you look right here, notice we did just a little bit of algebra, but notice we got a really nice, easy function because we don't have to apply the product rule here. All we got to do is the power rule, and we get the same exact answer as before. So if you can see something that you can simplify very quickly, by all means, do it, okay? Otherwise, you can always rely back on your rules that we learned. Let's try another one here. What number was this? 5? No, that was 4. Okay. So here's number 5. Now, this is a really nice problem. I love putting problems like this on a test. Okay. Now, with this situation, we have f of r equals 5 over r to the third. And we are forced to use some algebra here. Because if you notice, this is the first time where you got the variable in the denominator. Okay. So we are forced to go ahead and use algebra. So we're going to have to rewrite this as f of r equals 5 times r to the -3. And the reason why we have to do this, look at the rules that we have. Let me go back to our book real quick, okay? Because I want us to go ahead and I want us to look at that table of differentiation formulas. So here's our table right here. And as you'll notice, there's not one rule that says, hey, here's what you do with exponents, or here's what you do with functions of x that are in the denominator. I guess technically you could use the quotient rule, but do you really want to do that? I mean, the quotient rule, the math gets tough very quickly. But if you look right here, all right, what's this zoom math? Oh, look at that. That's nice. So if you look at this formula right here, all right, this says, hey, if you got an exponent, you can always pull the exponent out front and just subtract it from 1. So what I'm going to do is I'm going to look at that 5 over r to the third power, and I'm just going to rewrite it as 5r to the -3. Now, when I take its derivative, I'm going to write this one out. I take the derivative, I pull it out front, and I subtract the exponent from 1. So f prime of r is going to equal -15 r to the -4. So make sure you are very, very careful with this. Make sure you are subtracting 1 from the exponent. Don't write -2. It's -4. A lot of people will make that mistake. So make sure you are being careful. Make sure you're writing this stuff out sometimes until you get like really good with this. All right. Then you can quickly go ahead and find all your derivatives real fast. All right. I'm going to try 1 or 2 more. All right, let's try this one here. This is number 6. So this is going to be f of t equals the cube root of t over t minus 3. So as soon as I see this, I'm thinking quotient rule. So f equals, t to the 1/3 F prime is going to be 1/3 t to the negative 2 over 3. G is going to be t minus 3. G prime is going to be 1. Now, remember, the quotient rule, order matters, okay? So if you need to, go back into your table and find that quotient rule. So the quotient rule, just to recap, G F prime minus parenthesis F G prime all over G squared. So I'm just going to go ahead and just match everything up. G is t minus 3 times F prime, 1/3 t to the negative 2 over 3 minus parenthesis F is t to the 1/3 times G prime, which is 1, all over t minus 3 to the second power. And I'm not going to simplify this. This on a test question would definitely, or if this was on a test, it would probably say something along the lines of perform the derivative, do not simplify. And that's what we would have right here. And you're going to see that a lot. All right. Let's do another one where it looks like it's the quotient rule, okay? But we could be really clever with it. All right. So let's look at this one. I think we're on problem 7. So let's do h of t equals 2t to the 5th plus t to the 4th minus 6t all over t to the 3rd. Now, our gut reaction says, hey, go ahead and use the quotient rule. But if you look at that denominator, that is a monomial. And I know when I have a monomial, and boy, do I love monomials, because what I'm allowed to do is I can separate every single term by that monomial. And I can simplify this. So just by simplifying this, look how nice this turns out. I get 2t to the second plus t minus, now this is going to be, and I'm going to write it off to the right, this will be 6 over t to the second, which is really just 6t to the negative 2. And now when I go ahead and find a derivative, I'm going to get 4t plus 1 plus 6t to the negative 3. All right. Make sure, this is 12 plus 12t to the negative 3. So make sure this negative 6t to the negative 2, when you find its derivative, the negative 2 comes down out in front, and then you subtract it from 1. Negative 2 times negative 6 is positive 12. Negative 2 minus 1 is negative 3. So it's 4t plus 1 plus 12t to the negative 3 power. All right, for the last two examples, they're going to be word problems, and I'm going to do more word problems in a separate video. But this is number 63 out of your text. It's very straightforward. The equation of motion of a particle is s equals t to the third minus 3t, where s is in meters, t is in seconds. Let's go ahead and let's find A, B, and C. So first, the velocity and accelerations or acceleration as functions of t. So here's part A. Now, remember, s is displacement. However, from the previous section, we learned that the derivative of s is our velocity. All right? So the derivative of s equals v, which is going to be 3 t to the second minus 3. So right here is our velocity. Now, technically, this is v of t. All right? So velocity is done. Now let's go ahead, let's find acceleration. So the second derivative of displacement is going to be our acceleration, which is the first derivative of the velocity. So all I have to do is take the velocity and take the derivative again. In fact, let me write this out. So s double prime equals the derivative of v, which equals our acceleration. So v prime is going to equal 6t, which I'm just going to substitute in a and just say, okay, well, there's my velocity, or there's my acceleration right there. Now, like I said, technically, this is a of t. So we have our velocity function, we have our acceleration function. All right. So part A is done. Part B, the acceleration after 2 seconds. Well, since they want to know the acceleration after 2 seconds, we're going to be using A of 2, which is 6 times 2. So the acceleration is going to be 12 meters per second square, if you remember your units for acceleration. All right. Part C, I forget what part C was. Part C is the acceleration when the velocity is equal to 0. So this problem is it's a two-parter. First, all right, let's go back, let's read it. We want the acceleration when the velocity is equal to 0. All right. So the first thing we got to do is take the velocity and find, is that the velocity? Yeah. And find when does the velocity equal 0? Like, what time does that happen? So 0 is going to equal 3 t to the second minus 3. Then we add 3 to both sides. We get 3 equals 3t to the second. Divide both sides by 3. This is going to give us 1 equals t squared. Taking the square root of both sides, we get plus or minus the square root of t squared, which we know time always moves forward. If we can go backwards in time, that would be amazing. But the velocity equals 0. And I'll just write the number. At t equals 1 second. So then the second part of this, well, they wanted to know what is the acceleration when the velocity is 0. So a of 1 equals 6t, which this is just nothing more than a of 1 equals 6 times 1. So a of 1 equals 6 meters per second squared. So this is the really weird part about understanding like physics and stuff like that. Even though the velocity equals 0, what that means, all right, is that your object, in this case, it's a particle, all right, your object is at a this is gonna be so hard to. It's at a standstill. However, the change in acceleration is positive, which means this object could be changing direction. All right. So it could have been moving left, and then the velocity got to 0. The acceleration is pushing it to the other side. So it's moving the opposite direction. So I think a really easy way to kind of describe this, all right, is let's say this is t, and right here, this is s of t. This is our displacement, all right? The thing is, you know what? I'm not even going to go this far into it. I think it'll be easier if I just draw a simpler picture. Here's our particle right here, okay? Now, if our velocity is greater than 0 and the acceleration is greater than 0, then our particle is moving to the right and it's speeding up. It's getting faster, okay? That's case 1. Case 2. Here's our particle. All right, it's moving this way, so the velocity is greater than 0, so it's moving to the right, okay? However, the acceleration is less than 0. What that means is that the acceleration is moving in the opposite direction of the velocity, which means eventually, if this acceleration is larger than the velocity, this particle will end up slowing down, turning around, and moving in the opposite direction. Okay? So it's kind of like putting the brakes on almost. Like if you're driving in your car and you put the brakes on, you are changing the acceleration of your car and it slows down. That's what's happening here. All right? And then you have the other case where your object is moving in this direction. So your velocity is negative, which means it's just moving in the opposite direction. And if your acceleration is also negative, that means that your particle is getting faster, moving to the left. All right. So you got to think about, physics in terms of like direction and then forces being applied. Now, the last example I'm going to do deals with the biology question. So let me go ahead and let me steal that out of your book. And in this question, biologists have proposed a cubic polynomial to model the length of Alaskan rockfish at age A. So at any age A, okay? So L is going to equal, L stands for length. Length equals 0.0155 a to the third minus, you can read that, where L is measured in inches and A in years. Calculate DL over DA, evaluate it at A equals 12. So this little line right here with the A equals 12 just means to evaluate at A equals 12. So we're interested in a 12-year-old Alaskan rockfish. This should model approximately how the length or how large the fish is. All right. Then they want us to interpret your answer. All right. Now, this is probably my favorite question because I love to interpret answers. All right. So the first thing we need to do is find the derivative. All right. So let me write it the way they did. So DL over dA, in other words, the derivative of L with respect to A, is going to equal, I'm going to grab my calculator, all right, because, we got decibels and stuff here, and I want to mess with that. So I'll write it out first. 3 times 0.0155 A to the second minus 2 times 0.372 A to the first plus 3.95. And then the derivative of 1.21 is going to be 0. Now to clean this up, the derivative of the length with respect to the age is going to equal 3 times 0.0155, which is 0.0465 a to the second, excuse me, minus 2 times 0.372. That's going to be 0.744a plus 3.95. And we want to evaluate this when a equals 12. So all we got to do is just substitute 12 in for a and simplify. So this is going to equal, and I'm just going to pause this real quick and do it on my calculator real fast. All right, and if you substitute this in and you use your calculator, you should get 1.718. And what is the length in? Length is measured in inches, so this will be inches. So a 12-year-old fish, or a 12-year-old Alaskan rockfish should be, it's not going to be perfect, obviously, but it should be 1.718 inches. All right. Now, here is another amazing thing. All right. This, and I'm going to highlight this. This right here tells me that, remember, derivative is a rate of change. This is a rate of change. So not only does this give me like how large the fish should be at 12 years, it also tells me the length of the fish is increasing because our derivative is positive. So it is increasing at a rate of 1.718 inches per year. All right, and that is huge because it tells me how fast how fast is this fish actually growing. Now, we know as, the fish get older, They tend to lose weight, and then unfortunately they die. So this is just a model. It's not perfect, but it gives us an understanding of what's happening. And this lecture is already 55 minutes long, so I'm gonna just shut it down right here. Next video, I'm gonna do some more word problems, and I'm gonna start bringing in trigonometric functions and stuff like that. All right, so I'll see you in the next one.